There is a date circled on calendars inside the Pentagon, inside the White House, inside chip companies, inside car companies, and inside every hedge fund that trades commodities. November 10th, 2026. That is the day a one-year pause on some of the most aggressive rare earth export controls in modern history is scheduled to expire. If it expires quietly, almost nobody outside the industry will notice. If it does not, the global technology economy could feel it within weeks. Picture the headline that would run if it doesn't. China restores sweeping rare earth. Export controls. Defense contractors warn of production delays. AI data center buildouts face new material shortages. That is not a hypothetical dreamed up for shock value. It is the exact scenario multiple governments, multiple defense contractors, and multiple technology companies are actively planning around right now in the summer of 2026, months before the deadline even arrives. To understand why one date on a Chinese government calendar can shake Washington, Wall Street, and Silicon Valley all at once, you have to understand what rare earths actually are. They are not rare in the sense of scarce. They are rare in the sense of almost impossible to refine cleanly, cheaply, and at scale. 17 elements with strange names like neodymium, dysprosium, terbium, praseodymium, samarium, and erbium. Elements most people have never heard of, hiding inside almost everything that defines modern power. Fighter jets, missiles, submarines, satellites, electric vehicles, wind turbines, smartphones, robots. And now the data centers running artificial intelligence. China does not just have a lot of these elements in the ground. China built, over 4 decades, the only fully integrated industrial system on Earth that can turn raw ore into finished high-performance magnets at massive scale. According to the International Energy Agency, China accounted for roughly 61% of global mined rare earth supply and around 91% of global refining and processing capacity in 2024. Other assessments put China's share of magnet-grade rare earth processing even higher, above 90%, with finished magnet production concentrated even more heavily inside Chinese factories. That is not a supplier relationship. That is a choke point. Now picture an engineer named Marcus working for a mid-sized American company that builds components for defense contractors and AI infrastructure firms. His job used to be simple. Find the cheapest reliable supplier, place the order, keep the assembly line moving. That job does not exist anymore, not the way it used to. In June 2026, China's Ministry of Commerce tightened export controls on 10 American companies, barring anyone anywhere in the world from supplying them with certain Chinese-origin dual-use materials. 2 of those 10 companies were MP Materials and USA Rare Earth, the 2 firms Washington has been counting on to build an American rare earth supply chain from scratch. Beijing called it retaliation for earlier American restrictions on Chinese companies. Whatever you call it, the message was unmistakable. The exact companies the United States is funding to escape Chinese dependence are the same companies China chose to target first. That is not a coincidence. That is strategy. 2 days later, China's Commerce Ministry published a new rule that took effect July 1st, formalizing a public reporting and reward system for anyone who flags suspected violations of strategic mineral export controls. In other words, Beijing did not just tighten the rules, it built an incentive structure to catch anyone trying to quietly route around them. Around the same time, Japan confirmed that 2 of its citizens working for a major Japanese company had been detained in the city of Dalian back in May 2026, accused of smuggling goods tied to export restrictions, reportedly involving rare earth-related items. A major Chinese precision optics company was also hit with domestic enforcement action that same month. This was not an isolated shot at the United States. On July 24, 2026, reports confirmed China's Commerce Ministry had blocked shipments of dual-use materials to 14 companies inside the European Union. Within 5 weeks, Beijing had widened its restricted list across 2 of the largest electronics and hardware markets on the planet. China's leverage extends well beyond rare earths in the strictest sense. Multi-institutional analysis published in 2026 found China controls roughly 90% of global rare earth processing, alongside roughly 80% of global tungsten refining and around 60% of antimony production. That same analysis found that export controls introduced across 2025 and 2026 had triggered price spikes of up to 6-fold outside China in some material categories, while licensing approval rates for European firms had fallen below 25% in certain sectors. Researchers who study this pattern closely have made an important distinction. China is not weaponizing scarcity, because in raw reserve terms, China only holds roughly 1/3 of the world's known rare earth deposits. China is weaponizing control, tightening and loosening the tap in cycles that preserve its pricing power, extract diplomatic concessions, and slow down Western investment in competing supply chains before it can reach meaningful scale. For Marcus, sitting in a procurement meeting, none of this shows up as a single dramatic headline. It shows up as delay, A supplier who used to confirm a shipment in 3 days now cannot give a straight answer. A purchase order that used to take 2 weeks now takes 2 months, if it clears at all. Uncertainty is the real weapon here, more than any outright ban. Companies cannot plan around uncertainty. They can only pay more to hedge against it. Now zoom out to the company at the center of this entire story, MP Materials. MP Materials operates Mountain Pass in California, the only large-scale rare earth mine currently active in the United States, and the largest rare earth deposit in the Western Hemisphere. In July 2025, the Pentagon bought roughly a 15% stake in MP Materials for $400 million, making the United States government the company's largest shareholder. The deal also included a $150 million loan from the Department of Defense, a guaranteed price floor of $110 per kilogram for key magnet materials over 10 years, and a commitment that all magnets produced at MP's new facility would be purchased by defense or commercial buyers. This was the largest direct government intervention in the American rare earth industry in decades. It effectively turned the Pentagon from a passive buyer of finished parts into an equity owner and anchor customer across the entire upstream and midstream supply chain. MP is now building a second, much larger magnet manufacturing campus called 10X in Northlake, Texas, a $1.25 billion investment expected to push the company's total domestic magnet capacity toward 10,000 metric tons a year, once commissioning begins around 2028. Apple signed a $500 million agreement with MP Materials in 2025 for magnets built partly from recycled rare earth material, with $200 million paid up front, and shipments beginning in 2027. General Motors has been sourcing MP-made magnets for EV traction motors since 2025. MP even formed a joint venture with the U.S. government and a Saudi Arabian state mining company to build a rare earth refinery in Saudi Arabia, creating a second processing leg entirely outside both China and the American mainland. By the first quarter of 2026, MP's magnetics revenue had quadrupled year over year, and total company revenue hit $90.6 million. Then came the June blacklisting, and MP's stock dropped nearly 30% in a matter of weeks. Within a month, it had clawed almost all of that back. Investors seemed to understand something important. Being targeted by Beijing is now, in a strange way, proof of relevance. China does not blacklist companies that do not matter. USA Rare Earth is running a similar playbook from a different angle. Instead of starting with a mine, it started downstream, buying equipment once used by a major magnet manufacturer and installing it inside a 310,000 square foot facility in Stillwater, Oklahoma. In March 2026, USA Rare Earth commissioned its first commercial magnet production line, aiming to fulfill customer orders for high-grade sintered neodymium iron boron magnets by the second quarter of 2026. The company is targeting roughly 600 metric tons of annual capacity by the end of 2026, doubling to around 1,200 metric tons by early 2027, with a long-term goal of 10,000 tons and full metallization capability. The federal government has backed this effort with roughly $277 million in direct CHIPS Act-related support, plus loan guarantee availability exceeding $1 billion. Private investors have poured in roughly $1.5 billion since 2022. None of this comes cheap, and none of it happens fast. USA Rare Earth posted nearly $300 million in operating losses in 2025 alone, the price of building an industry from a near-standing start. Here is the uncomfortable truth underneath all of these announcements. Mining rare earth ore is actually the easy part. The hard part, the part China spent 40 years perfecting, is separating 17 chemically similar elements from each other, refining them into pure oxides, converting those oxides into metal alloys, and pressing those alloys into finished, heat-resistant, high-strength magnets that can survive inside a missile guidance system or a fighter jet engine. The United States government has openly acknowledged that limited domestic processing capacity has historically forced some material mined on American soil to be shipped overseas for refining before it can even come back for use at home. Building a full mine-to-magnet supply chain is not something you do with a press release. It requires specialized separation plants, trained metallurgists, environmental permitting, alloy production lines, and years of construction, often a decade or more from first shovel to first shipped magnet. Morgan Stanley's 2026 research on humanoid robotics and materials put the average global mine development timeline at roughly 17.8 years. China is not standing still while the West tries to catch up. And nowhere is the pressure building faster than inside the story nobody was originally telling about rare earths, the story about artificial intelligence. AI looks like software from the outside, but underneath every chatbot and every model lies an enormous physical machine. Data centers full of racks, servers, cooling systems, power equipment, and miles of fiber optic cable. Some of the rare earth elements least discussed in the mainstream press turn out to be quietly essential to that physical machine. Erbium is one of them. used to dope fiber optic cables so they can carry AI data over long distances without the signal degrading. In July 2026, erbium prices spiked amid fears that China could restore broader export restrictions once the US-China trade truce approaches its expiration. By early July 2026, erbium oxide on the Shanghai Metals Market benchmark had climbed more than 20% in a single month. By August, erbium was the standout gainer in an otherwise cooling rare earth market, rising nearly 18%, even as most other heavy rare earths pulled back. Analysts noted that erbium's demand is tied specifically to telecommunications infrastructure rather than magnet applications, which is exactly why it moved differently, and exactly why it is being watched so closely by anyone building AI infrastructure. The optical transceiver market that depends on materials like erbium and germanium is projected to roughly triple in size by 2030, driven almost entirely by AI data center expansion. Germanium prices had already surged toward $5,000 per kilogram in late 2025. For a company planning to spend hundreds of millions of dollars on a new AI data center, the chips might be secured, the land might be secured, the power contract might be signed, and yet a shortage of a niche fiber optic dopant most executives have never had to think about could still slow the entire build-out. That is the terrifying part of this story for the technology industry. The AI race was supposed to be about who has the best model, the most chips, the most capital. Increasingly, it is also about who controls the raw materials sitting quietly inside every mile of cable and every optical amplifier that makes a data center actually function. Picture a hyperscale technology company breaking ground on a new campus with the land secured, the power purchase agreement signed, and billions of dollars in chip orders already locked in. Then, a single line item buried deep in the procurement schedule, specialty optical fiber components dependent on erbium and related dopants, start slipping. Not because the company did anything wrong, but because the refining capacity for that one obscure material sits almost entirely inside a handful of Chinese facilities that can be redirected, taxed, or licensed more slowly at the direction of a single ministry. Multiply that one delay across dozens of data center projects racing to come online in 2026 and 2027, and you start to see why critical minerals researchers have started calling supply chain risk the number one hidden threat to the pace of the entire AI build-out. Now bring the defense industry back into the frame, because nowhere is the vulnerability more visible than inside America's most expensive weapons program, the F-35 fighter jet. According to open source engineering estimates, each F-35 contains somewhere around 400 kilograms of rare earth material. Neodymium and praseodymium power the flight control actuators and targeting systems. Samarium bonded with cobalt forms magnets that can survive the extreme heat inside the engine's power systems in an alloy where an ordinary magnet would simply lose its strength. Dysprosium and terbium are doped into those magnets in small quantities specifically to keep them functional under combat heat. Yttrium coats turbine blades with a protective ceramic layer. In September 2022, the Pentagon quietly halted new F-35 deliveries after discovering that a small magnet inside the engine had been made using a Chinese-origin alloy, a violation of American defense procurement law. The issue did not compromise the jet's performance, but it exposed something far more important, that America's most advanced fighter aircraft still runs, in part, on materials the country does not fully control. Virginia-class submarines reportedly contain more than 4 metric tons of rare earth material each. The Congressional Research Service has documented similar exposure across drones, radar systems, and precision-guided munitions. The Commerce Department has determined that the United States remains almost entirely import-dependent for the highest-grade rare earth magnets used in military-grade applications. That is the backdrop, against which every MP Materials contract, every USA rare earth production line, and every G7 mineral pact needs to be understood. Because this is not really a story about a commodity market. It is a story about whether the country that builds the world's most advanced weapons can actually source the materials those weapons are built from. The United States is not doing this alone. In June 2026, G7 leaders meeting in Evian-les-Bains, France, launched a coordinated critical minerals alliance aimed squarely, if not always by name, at reducing dependence on China. The stated target: reduce reliance on any single supplier outside the G7 and its partner countries for rare earths and permanent magnets to below 60% by 2030, with a longer-term ambition of 50%. The declaration noted that 195 projects had already launched since the start of 2026, attracting 64 billion euros in investment across mining, processing, recycling, and magnet manufacturing. An earlier version of the alliance, launched in 2025, had already mobilized $6.4 billion in investment across 26 separate projects. Analysts at multiple research firms have been blunt about how difficult that 60% target really is, given that China currently controls somewhere between 85 and 90% of global rare earth separation and magnet manufacturing capacity. Reaching those targets requires new separation plants, new alloy production lines, thousands of trained workers, faster permitting, and sustained financing over years, not months. The United Kingdom has rolled out its own parallel strategy, aiming to meet at least 10% of mineral demand domestically and 20% through recycling by 2035, while capping any single country's share of critical mineral imports at 60%. The European Union's Critical Raw Materials Act sets a similar 65% dependency ceiling. Every one of these numbers points to the same underlying admission. Governments now treat rare earth dependence the way they once treated oil dependence, as a strategic vulnerability that has to be actively managed, not a market inefficiency that will simply correct itself. The G7 declaration also committed member nations to sharply increasing recycling rates for critical raw materials, with a goal of building collective recycling capacity, capable of covering a meaningful share of annual G7 consumption by the end of 2030. Leaders further agreed to promote coordinated demand aggregation, pooling purchasing power across allied nations so that no single country has to negotiate alone against a dominant supplier, and to task ministers with setting additional dependency targets for other critical minerals before the end of the year. Some analysts have pushed back on how these strategies are being implemented, warning that governments risk labeling too many materials as critical all at once, which dilutes political focus and funding away from the handful of elements like neodymium, dysprosium, and terbium that actually matter most for magnets, defense systems, and AI infrastructure. The concern is less about ambition and more about execution, because pledges on paper do not refine a single kilogram of neodymium, and permitting reform, skilled labor, and long-term offtake financing all move far slower than a diplomatic communique. And then there is the demand side of the equation, which almost nobody was talking about 2 years ago and everybody's talking about now: robots. Specifically, humanoid robots. IDTechX forecasts global rare earth magnet demand climbing from roughly 190,000 tons today to somewhere near 330,000 tons annually by 2036, with electric vehicles, wind turbines, and robotics as the three primary growth engines. Morgan Stanley's 2026 research on humanoid robotics estimated that each next-generation humanoid robot requires roughly 0.9 kilograms of neodymium-praseodymium magnet material, and that global humanoid deployment could push total rare earth magnet demand up by as much as 167% by 2050. One widely cited estimate from Adamas Intelligence noted that a single humanoid robot needs 30 or more individual motors, almost all of them built around rare earth magnets, with no current alternative technology matching their power density. If ambitious industry targets for humanoid robot deployment over the coming decades are even partially realized, some analysts have calculated that global magnet output would need to expand by well over 100 times current levels just to keep pace. NdPr oxide, the core feedstock for these magnets, has already swung wildly, moving from around $60,000 per metric ton to more than double that within about 18 months, driven by exactly this collision of electric vehicles, wind power, and now robotics, all competing for the same constrained Chinese-dominated supply. China is not sitting on the sidelines of this robotics race either. Industry projections, cited by materials researchers, suggest Chinese humanoid robot output alone could reach nearly 60 million units by 2050, with domestic manufacturers racing to control both the robots and the magnet supply chain feeding them. Tesla has signaled plans to unveil a third-generation humanoid robot, and consumer electronics manufacturers in China are expanding robot assembly capacity of their own, meaning the same rare earth magnets are now being fought over by American defense programs, American AI data centers, and Chinese robotics manufacturers simultaneously. Every one of these applications, AI data centers, fighter jets, electric vehicles, wind turbines, and now robots, is drawing from the same narrow, concentrated pool of refining capacity. That is what makes November 10th, 2026, such a critical date to watch. It traces back to October 2025, when China announced sweeping new export controls covering additional rare earth elements including samarium, gadolinium, lutetium, europium, and ytterbium, along with new extraterritorial rules that would have let Beijing regulate the use of Chinese origin materials, even in products made outside China. Days later, at a high-stakes meeting in Busan, South Korea, Presidents Trump and Xi agreed to a one-year truce, suspending those October controls and easing earlier restrictions on gallium, germanium, antimony, and graphite, in exchange for tariff reductions and other concessions. President Trump described it as a deal that would be, in his words, routinely extended as time goes by. Other observers were less confident. One former U.S. ambassador to China called it an uneasy truce in a long, still simmering trade war. Analysts at Piper Sandler suggested that China, not the United States, came out of those negotiations holding the stronger hand, given how much leverage rare earths still provide. As of mid-2026, key elements of that truce, including the suspended October controls and other restrictions on gallium, germanium, and antimony, were still scheduled to lapse in November, unless both governments agreed to extend them again. That is the reason financial analysts, defense planners, and AI infrastructure executives are all watching the same date on the calendar. If the truce holds, the current uneasy stability continues. If it does not, a second wave of restrictions covering holmium, erbium, thulium, europium, and ytterbium could take effect, hitting exactly the elements tied to lasers, advanced optics, and the fiber optic backbone of AI infrastructure. Meanwhile, the United States is not waiting to find out which way it goes. In August 2026, the Pentagon's Office of Strategic Capital committed up to $400 million in a conditional 25-year loan to Sunrise Energy Metals, an Australian company, to build what both governments are calling the world's first primary scandium mine near the town of Fifield in New South Wales. Scandium, when added to aluminum in small amounts, produces alloys that are dramatically stronger and lighter, useful in aerospace and defense applications, and increasingly relevant to advanced telecommunications equipment. Currently, scandium exists almost entirely as a byproduct of other mining operations, with no dedicated primary mine anywhere in the world, and foreign producers heavily concentrated around China, controlling roughly 80% of global mining output and nearly all global processing. In exchange for the loan, the Pentagon secured a right of first offer on the mine's future output. Lockheed Martin had already signed a deal to purchase a quarter of the mine's scandium production for its first 5 years of operation. Shares in Sunrise Energy Metals jumped nearly 30% on the news. This is not an isolated deal. It is part of a much broader pattern. The Council on Foreign Relations estimated that from January 2025 through June 2026, the U.S. federal government had invested roughly $10 billion across the critical mineral sector as a whole. Recycling is emerging as another front in this effort, with Microsoft backing a startup that recovers rare earth metals from old hard drives, and separate feasibility work underway for a $125 million rare earth magnet recycling facility inside the United States. Apple's $500 million deal with MP Materials specifically includes magnets built from recycled material, a sign that even the world's largest technology companies are now treating rare earth supply security as a problem worth solving directly, rather than a risk to simply absorb. So where does all of this actually leave Marcus and companies like his? And honestly, where does it leave all of us? For decades, globalization ran on one simple question: who can make this the cheapest? Companies chased low-cost manufacturing wherever it existed, and rare earth processing concentrated in China because China was willing to build the industrial capacity, absorb the environmental cost, and subsidize the industry for 40 straight years, while almost nobody else bothered to compete. Now, governments in Washington, Brussels, Tokyo, Canberra, and London are all asking a very different question. What happens if our cheapest supplier turns out to be our biggest strategic rival? That single question is reshaping trade policy, defense procurement, and industrial investment on a scale not seen since the oil shocks of the 1970s. To be clear, none of this means American defense production is about to collapse, or that the AI industry is on the verge of grinding to a halt. The current Chinese restrictions remain targeted rather than total. Licenses are still being issued for many transactions, and companies across multiple industries are actively adapting, diversifying suppliers, signing new offtake agreements, and investing in recycling. But the deeper lesson is impossible to ignore. China still holds enormous structural leverage over a set of materials that sit inside almost every advanced technology the world depends on, from the F-35 sitting on a runway to the data center training. The next generation of AI models to the humanoid robot prototypes rolling out of factories in Shanghai, Austin, and Fremont. The next phase of competition between the United States and China will not be decided by tariffs on finished goods alone. It will be decided in mines in California and New South Wales, in separation plants in Texas and Oklahoma, in magnet factories racing to reach commercial scale, in fiber optic supply chains few people ever think about, and in the electricity grids and industrial ecosystems tying all of it together. Whoever controls that physical foundation, mines, refineries, magnets, chips, and the data centers built on top of them, may hold a decisive advantage in determining who actually leads the next era of defense, technology, and global economic power. Mark November 10 on your own calendar, because whatever happens on that date will not stay contained to a commodities market or a trade briefing. It will move through defense contractors, through AI infrastructure budgets, through the price of your next phone, and through decisions being made right now in boardrooms and government offices on 3 different continents. There's also a quieter, longer story running underneath all of this, the story of the American national defense stockpile. For most of the 20th century, the United States kept large government reserves of strategic materials, specifically so that a foreign supply shock could never halt a war effort or a defense production line. That stockpile system atrophied for decades as globalization made just-in-time sourcing look cheaper and smarter. Rare earths are now forcing a rethink of that entire philosophy, with lawmakers and defense planners openly discussing new stockpiling programs, strategic reserves, and guaranteed offtake agreements that function almost like insurance policies against exactly the kind of export shock China demonstrated in June 2026. Some of these programs already exist in early form, buried inside Defense Logistics Agency contracts, supporting companies working on rare earth metallization and alloy production, the unglamorous middle step of the supply chain that converts refined oxides into usable metal. It is worth remembering that Washington is not the only government treating this as urgent. Japan tightened its own controls on dual-use exports involving certain rare earth-linked technologies to specific entities beginning in January 2026. A reminder that Beijing is not the only government using export policy as leverage in this contest. Meanwhile, companies in Vietnam, Malaysia, and elsewhere in Southeast Asia have quietly expanded rare earth processing capacity of their own, positioning themselves as alternative midstream partners for Western buyers who no longer want all of their materials touching Chinese soil at any point in the supply chain. None of these alternatives can match Chinese scale yet, not even close, but each new facility chips away, however slowly, at the idea that there is no other way to do this. Step back far enough and a clear pattern emerges across every single thread of this story. A Pentagon that used to buy finished weapons is now buying equity stakes in mines. An AI industry that used to worry only about chips is now worried about fiber optic dopants sourced from a handful of Chinese refineries. A car company and a smartphone company are now signing decade-long magnet supply contracts the way oil companies once signed drilling rights. A diplomatic handshake in South Korea is now something commodity traders track as closely as a central bank meeting. None of that was true 5 years ago. All of it is true now. The rare earth story used to be a niche topic for mining analysts. In 2026, it became one of the central fault lines of the global economy, and it is not going away anytime soon.